Compound characterization, infrared spectroscopy, example spectra. In this webcast, I'll be showing you a number of IR spectra. The purpose of this webcast is to demonstrate how even small changes in the structure of a compound can have large consequences in the associated infrared spectra. You will see how stretches that we discussed in the previous webcast actually look like in a real infrared spectrum. Here we have two molecules, hexane and 1-hexene. Hexane contains many sp3 hybridized carbons connected to hydrogens, and as we can see, at below 3000, we see stretches that correspond to the sp3 hybridized carbons attached to hydrogen. If we compare hexane to 1-hexene, we still have many sp3 hybridized carbons attached to hydrogens, and we still see stretches below 3000 that correspond to that. We also have, however, sp2 hybridized carbons attached to hydrogens. Those should appear above 3000, and in fact, we do see stretches above 3000 that correspond to those sp2 hybridized carbons attached to hydrogen. We continue on and compare 1-hexene to 1-hexyne, which has an alkyne. We see that we have an sp hybridized carbon attached to a hydrogen. That should show up at roughly 3300 wave number, and indeed we see that in the IR spectrum. We see this stretch, which corresponds to this sp hybridized carbon attached to a hydrogen. Now let's compare the spectrum for 1-hexyne to the spectrum for 2-hexyne. Both have alkynes, but they are different in a key way. Notice how 1-hexyne has an sp hybridized carbon attached to a hydrogen, which is why we see this stretch in 3300 wave number area. 2-hexyne does not have that bond. The carbons in 2-hexyne are both bonded to carbons. There is no sp hybridized carbon attached to a hydrogen. That is why this signal here is not present in 2-hexyne. If you look at roughly 2200, we see a stretch here. That is the carbon-carbon triple bond stretch. You see that same stretch down below. Notice, however, that the stretch for 2-hexyne is much weaker than the stretch for 1-hexyne. This is because the alkyne in 2-hexyne is more symmetric, has a much smaller change in dipole moment than 1-hexyne. Therefore, we have a correspondingly smaller signal in the IR spectrum. Now let's start adding non-carbon functional groups. Up top we have hexane once again, and down below we have hexanol. Hexanol has an alcohol, has an OH bond. Notice how this has a very obvious consequence. The IR spectrum for 1-hexanol has a very strong, very broad stretch in the 3400 wave number area. If we change that alcohol to an amine, in this case a primary amine, we see a stretch in the same area, but it's much smaller compared to the alcohol stretch, and it also has a different shape. We see that there are two peaks to this stretch. This is how you can distinguish an OH from an NH using IR spectroscopy, even though they appear in the same place. An OH is very large, very broad, whereas an NH tends to be much smaller. A primary amine tends to have two peaks, secondary amines tend to have only one peak. Now let's compare hexanol to hexanal. We've gone from an alcohol, an OH, to a carbonyl. As you can see, the OH stretch has disappeared in hexanal because there's no OH present. However, we now have a new stretch at 1700 wave numbers. This new stretch corresponds to the carbonyl. As you can see, it is quite strong, which is characteristic of carbonyl stretches. Compare hexanal to hexanone, we go from an aldehyde to a ketone. Let's look at these carbonyl stretches. These are incredibly similar. There's no way you will be able to distinguish the aldehyde from the ketone based on the carbonyl stretch. They are too similar. This is why I emphasized in the previous webcast how you cannot use the location of a carbonyl stretch to determine what type of carbonyl is present. You can, however, use a different stretch, which I did not talk about earlier, because it sometimes shows up and sometimes doesn't, but it can be useful. If you look at the structure for hexanal, we have a unique CH stretch. This hydrogen attached to the carbonyl carbon, that bond is special. That shows up in a particular location in a particular shape, which we can see here. This is often called the Fermi doublet. Again, it doesn't always show up, and even if it does, it might be covered up by other stretches. Don't rely on this appearing. However, if it does appear, this Fermi doublet is characteristic of an aldehyde. See how we see those stretches here, but not in the ketone. Now let's compare the aldehyde to an ester. We again see two stretches in the carbonyl region that are very similar. You would not be able to tell which of these was the aldehyde or which of these was the ester based solely on the carbonyl stretch. Now let's compare the ester to the acid. As you can see, the acid has two bonds that contain oxygen, a carbonyl and the OH. As you can see, both the ester and the acid have a carbonyl stretch because they both contain carbonyls. However, only the carboxylic acid contains an OH, which is why only the IR spectrum corresponding to the acid contains this broad OH stretch. This is the end of the example IR spectra for this webcast. These were good examples to use to show you how the presence or absence of a functional group in a molecule can greatly affect what you see in an IR spectrum. The ability to determine what stretches are or are not present will be crucial to your success in interpreting IR spectra.